All right, so in this video, we're going to go over the different types of Bronsted acids, and these fall into four different categories. The first is HX, where H just represents anything that doesn't contain um, OH, an OH group, okay? Um, then there are three other different types of Bronsted acids that all have an OH embodied in them somewhere. And so the first of those is called an aqua acid. And these are acids where the acidic proton is on a coordinated water. And so, it'll look something like this. Usually you'll have coordinated means coordinated to a metal, bound to a metal. So you have a water bound to a metal. I'm just showing a generic metal with simple M. Usually it's a metal. It can be metalloid as well, or in some other cases non-metals, but usually we're talking about metals here. So I've just been using M here on this slide. So anyway, that water, one of these waters will react with water and free water. A proton from that coordinated water will get transferred to it and make hydronium ion, which of course is an acid. So that proves to you that this aqua acid is indeed an acid, and it'll give you MOH minus. The next type is a hydroxo acid, and this is when you have an acidic proton on an OH group again, but there's no neighboring oxo group, okay? So instead of being a coordinated water, here it's on an OH group, okay? But there's not a neighboring oxo group, okay? That distinguishes it from an oxo acid. So this is a hydroxo acid. And so this would look something like an OH coordinated to a metal and then reacting with water to become MO. Okay, so this H just went away and formed with water hydronium ion. Oxo acid is the last one. Oxo acid, you have an adjacent oxo group, and the acidic proton is coming from an OH. So it would be something like MOOH. Okay, and the OH is again going to become an O minus and make hydronium from that H going to water. So aqua acid, these are sort of a series, as we'll see on the next slide. Aqua acid, water coordinated. Hydroxo acid, OH coordinated, nothing else nearby, that's O. Okay, oxo acid has an O next to an OH, okay? And so here are some examples. HX, so this doesn't have any OHs around or waters around. So HCl would be an example, hydrochloric acid or hydrocyanic acid, HCN. Aqua acid example would just be iron coordinated to 6 water molecules. And so, one of those water molecules can become acidic and make OH minus in the process. So this was a 3+ iron species at first, and now it's a 2+ because it gave up one of its protons to make water, positive 1 charge, H3O+. Hydroxo acid, here's an example, tellurium hydroxide, okay, where you have 6 hydroxides coordinated to tellurium, and so there's no oxo groups, no O groups near this. This is why it's a hydroxo acid, and one of these OH minuses gets deprotonated to make an oxo group, O minus, okay, and that in turn, that proton went to making hydronium. And then an oxo acid, here's an example. This would be actually hypochlorous acid, okay, HCl2. Oh, that would be actually, sorry, that would be chlorous acid. But anyway, the name isn't important. The key point is, why is this an oxo acid? Because it's an OH next to an oxo, next to an O group. So what ends up happening is this OH gets deprotonated, okay, and the proton joins the water molecule to make hydronium, and you end up with the deprotonated. Now you have 2 oxo groups next to one another, making the chlorous anion. So you can think about aqua acids, hydroxo acids, and oxo acids as being related. This is why it's useful to have these terms in the first place. And they're just successive deprotonation. So to go to a hydroxo acid from an aqua acid, you're going to get lose a proton. And if you go from a hydroxo acid to an oxo acid, you're going to lose a proton further. So here's the way to look at this. Aqua acid, here's going to be one compound that does this whole series. So we start out as an aqua acid. This is a ruthenium complex bound to two water molecules. Why is an aqua acid? It doesn't have any neighboring oxo groups, right? And so it's just bound water, okay? And so it doesn't have any neighboring oxo groups, and it doesn't have any hydroxides. So it's just bound water, just bound water, aqua. I mean, that naming is nice, okay? Aqua means water, right? So what's going to happen is here actually two protons are being deprotonated. So both of these water molecules are going to make hydroxide. As you can see, you make two hydronium ions as a result, and this charge of the complex went down from 4+ to 2+ because you lost two protons. This, okay, these are the same. I just moved it over. What you made there is actually a hydroxo acid. Why? Because it has hydroxo groups. That's where the name hydroxo acid comes from, but no oxo groups involved. Okay, there's no neighboring oxo groups. And so this can undergo a one proton event where one of these hydroxides loses a proton, and in the process, right, it went from 2+ to 1+ because it lost a proton, made hydronium, and that hydroxide group became an oxo group. So now you have an oxo acid, okay? So you did this whole series, aqua acid, from hydroxo acid to oxo acid. Now you might be wondering, how did I get a double bond there? There's just a resonance structure that makes this work. And so think about deprotonating this. That's going to get you O-, okay? And it'll be O- 2+. Well, that's the same thing if you draw a resonance structure as making the whole thing plus, right? And just bringing down a lone pair and making a double bond. And so that's why you get a double bond right there.